Today, the last day, we were learning about the Heisenberg picture as opposed to the Schrödinger picture. So the Heisenberg picture, the difference was in the Schrödinger picture, we had psi depends on time, and mostly the operators do not. And if the operators do not, the basis vectors also do not. Huh? So the basis vectors. While in the Heisenberg picture, psi stays put, it doesn't change, and the operators change with time. So these two are actually equivalent pictures of the dynamics. We call it picture. Different ways of viewing something, but what we are viewing is the same thing, and the results we got are essentially the same. So we have seen that in the Schrödinger picture, you have the psi s, which is a function of t, will be some u operator times psi s at time 0. Okay, and the u operator we have learned in the last class, the time evolution operator is e to the power minus I, the Hamiltonian operator t by h cross. Then we said that in the Heisenberg picture, we say that the psi in the Heisenberg picture, we do not put function of time because we are deliberately positioning things in such a way that it will not depend on time. So then we say u dagger of the psi s, so that when you put u dagger u together, you basically get the starting value. So this one does not change. So this is equal to psi. This is at any point in time. Sorry. Time, and this is at 0. So it does not change, psi does not change, and our u dagger was positive I h operator t by h. This is what we learned, and we also learned that the Heisenberg equation of motion, which is basically something that tells us how the operators change with time, that we obtained as the derivative of the operator, derivative of any operator A in the Heisenberg picture, that we obtained as 1 by I h cross that A, how it commutes with the Hamiltonian operator. There was a plus in the Heisenberg picture. So this is what we had obtained, and obviously this term will be 0, if there is no explicit time dependency. Okay, so for most cases, in fact, you will find this equation in most books. Uh, this equation in most books, sorry. Uh, because most books actually assume that this A operator is not dependent on time. For example, if you have a situation with the harmonic oscillator or the infinite square well, then the Hamiltonian is not dependent on time. So the operators will also not have any explicit dependence on time. Now, these are in many senses the equivalent representations of the same thing. But you might ask, what happens to the kets? I have already shown that the ket of the psi, that means the state ket, does not change with time. But what about the other kets? For example, the base kets. Now, the base kets obviously will depend on time in the Heisenberg representation. But let's see how it does. Let's consider an eigenvalue equation. Because the eigenvectors are normally the basis, so we need to figure out whether the eigenvectors change and how they do. So let's consider a eigenvalue equation. A operating on a vector A is giving the eigenvalue A times the vector A. It's eigenvalue equation. Now, in the Heisenberg picture, you have the A H. This will be U dagger A U. Okay, this is what we learned in the last class. And U is given as I just wrote there. This can be written as at time 0. Yeah. Now, at time t0, obviously the two pictures will coincide. Now what we start with is this, and then we operate with U dagger from the left. So I'll give some gap. Operating on the A is equal to A. This was the equation, and I first operate with the U dagger from the left. So I have to operate U dagger from the left. A, this number is a eigenvalue, therefore number. So I can bring this here. So I'll bring this to the right hand side, and I'll write now in this gap you can put 1, and 1 is since U and U dagger, U is a unitary operator, and therefore we can put U dagger here, and as a result this becomes the A in the Heisenberg picture. Okay, now this then I'll put in a bracket U dagger A is equal to A times U dagger A. Obviously, for the Heisenberg operator, or the operator in the Heisenberg picture, U dagger A is the eigenvector. So this is the eigenvector. Eigenvalue remains the same, but the eigenvector changes. And since U dagger has a time dependence. Therefore, the eigenvectors are also time dependent. You might, in your mind's eye, picture things like this. Suppose I have a coordinate system like this. I'm just drawing 2D, so easier to picturize. And I have the vector psi like this. Now, in the Schrodinger picture, this guy rotates, okay? And this guy rotates because it is multiplied by a unitary operator. It rotates, keeping its magnitude constant. So effectively, it rotates like this. And in the Heisenberg picture, it does not rotate. Instead, the base gates rotate. And in order for the projections to remain the same, the base gates have to rotate in the opposite direction. That is why you will find that psi is multiplied by u, and the base gates are multiplied by u dagger, which means that it actually rotates in the opposite direction. So after some time, this will remain fixed, but the basis will become like this. And in that basis, so this has actually moved to this position. So this has actually moved to this position. And naturally, the projections will, we need to worry about what the projections will be in the next new representation. So what will the projections be? The projection, the expansion coefficients, the expansion coefficients let's call it C in this direction A, which will be now a function of time. This will be normally obtained by the projection of the sine vector on the eigenvector. So it is actually the A here and the psi as a function of t here. Now the psi, you know, is A, and this is u operating on psi at t equal to 0. We normally don't write like this, but let me write like this so that it will be clearer to you what I'm talking about. So u operating on psi, u operator operating on psi, that is the current value of psi in the Schrodinger picture. In the Heisenberg picture, so this is in the Schrodinger picture. In the Heisenberg picture, the expansion coefficients are exactly the same thing, A psi, but in this case, A is changed with time. And we have seen that the eigenvector becomes now u dagger A. Now, this is when it operates on the ket, but now it has to be operated on the bra, so it becomes A u. Okay, so then it becomes exactly this, and then this is our psi. Psi at t is equal to 0 because psi doesn't change. You can write it in the same way. So you see, we get exactly the same things in the two cases. So the projections do not change with time. This is an important revelation that we had. Okay, good. So let's now. This is all fine, but one nagging doubt you may have is that how actually to use it. How did Heisenberg actually used it? By the way, I can tell you that Heisenberg was actually doing it in somewhat guesswork way, and this equation was actually derived by Dirac, but he named it Heisenberg equation of motion courteously, because it was the way Heisenberg tried to picture things. He just filled in the missing piece of information that this is how it will be evolving. But something like that Heisenberg was also doing sort of intuitively. So in order to show how actually, if you forget about the Schrodinger picture, if you want to work out the whole thing, for example, something like the harmonic oscillator, using the Heisenberg picture, then how would you proceed? Let us try to work it out. Where do we start? No, I need the space. So let me clear it off. Only I'll keep this one because I'll use this equation. If you are using the harmonic oscillator, this term will of course not be there, so I can delete it. So let us illustrate how actually this can be used using an example that you already more or less know. So we take the harmonic oscillator. And you know harmonic oscillator, the Hamiltonian is p square by twice m. Px, I'll write because we are considering plus half m omega square x square. So this is how it was. So this will become a operator. So that was the Heisenberg's Hamiltonian operator. And now we need to operate on this. So first we are trying to figure out what will be our x operator. This is what we are trying to find out. In order to find that out, we'll have to substitute in place of a, we'll have to substitute x. I'm trying to figure out what will be x in the Heisenberg picture. Okay, so we will say that dx dt IH cross, I'll bring it here, IH cross is equal to, then this will become x comma the Hamiltonian. And the Hamiltonian operator has two components, so we can break it up as this is 1 by 2m, 1 by 2m. It will be x operator, comma, this is px, plus it will become half m omega square. Now this will become x operator and the x square operator. Obviously, x commutes with x square, so this term will go to 0. I can now delete this so that we can have some space. So we are left with this, and this is something that we had in one earlier class we had calculated. So this is something we had earlier calculated. If you recall, we had calculated, I'll just write it here so that we do not have to do it all over again. X px square is equal to twice I h cross px. This is what we had earlier calculated. Quite some time back, you can open your class note, you will find it. So we'll just substitute it here. So is equal to 1 by twice m. Here is twice I h cross px operator. Cancels off. So this becomes an I h cross cancels off. I h cross. So this becomes px operator by simple. So much so good. Similarly, we can also find the operator for p and its equation. So it will become IH cross TPX dt is equal to, in this case, px operator commuting with this, and in this case it will become again this, so 1 by twice m, this will contain, it will be px square comma h operator, and then plus half m omega square, then it will become uh, px comma x operator square. Sorry, this will become, I have written wrongly. It will become the px square. Px with px square. So px comes from here and px square comes from here. And this obviously is 0 because px commutes with px square. And this term, we had again calculated it earlier. This term will was px x square. If you recall, we wrote it as px x x x x px, and then we substituted, and that way we calculated. And this can also be easily calculated. You can do it very quickly. So this will become is equal to twice I h cross x. So this is, the whole thing becomes simply half m omega square into twice I h cross x, cancels off. So it gives us is equal to let me see, did I write this? Okay, fine, let us continue. I have to bring the IH cross from here. So dpx dt is, I'll put 1 by IH cross, and then this term half goes m omega square I h cross x vector. This is of is equal to m omega square x. Did I miss a minus sign somewhere? Did I miss a minus sign somewhere? Yes, I missed a minus sign here. It has a minus sign. So this will have a minus sign. Okay, so we have obtained the equations for both dx dt and dpx dt, and we can now take a derivative again of this and substitute this, so that d2x dt2 is equal to 1 by m dpx dt is equal to, now I substitute it here, 1 by m. It is then minus m omega square x operator, and cancels off, is equal to so we can write it now as a equation like d2x dt2 plus, I'll bring it here, omega square x equal to 7. Let us name it 1 because I'll need it later. So this equation looks familiar, like our uh, usual harmonic oscillator equation. The only difference is that now this is an operator. Operator means it is actually a matrix. So it is a matrix differential equation that we obtain. Now, this matrix differential equation, this will be applicable to each term in that matrix. So we can write this as x double dot in the mnth location of the matrix. This will be a function of time plus omega square, and this is x mn in the matrix. This will also be a function of time equal to 0. Okay. So this is an equation that we have. I'll better use this as my numbered equation because this is what we actually need. And you might say that we'll simply solve this differential equation and find the xmnth term. Yes, you can do that, but there are easier ways of doing it. Now we know that for each of these eigen functions, psi nth eigenfunction, psi n, it will be function of x and t. It will be psi n at time equal to 0. So x comma 0 e to the power minus I e n, the nth eigenvalue, times by 8 plus. This is something that we knew earlier. So if you have an operator, for an operator, some operator A, the matrix elements are, this is something that we have learned, the matrix elements are A mn, mnth element, a function of time, will be the psi m a psi n. This is something that we know, right? These are the matrix elements. And the psi m will evolve like this, psi n will evolve like that, and therefore we can write in place of psi m, we can substitute something like this. In case of psi n, we can substitute like that. But now, notice that when you do it for the bra, this will have to be conjugated. So this will become plus, and so on and so forth. So this, we can easily bring this out. So in fact, we could have done that, but let me write it. It will be psi m at 0. I'll just shorten it. I'll not write x and 0. Times e to the power I e m t by h cross a. It will be psi n at 0 e to the power minus I e n t by h cross, and therefore we get e to the power I, it will be e m minus e n t by h cross times, here it will be the initial. So basically this will give you the initial A. So let me simply write it as A at the initial time, A operator at the initial time, mnth term at time t is equal to 0. Okay. So this is true for any operator. This will be true for the position, this will be true for momentum, this will be true for everything. And let us abbreviate this by saying that let us call omega mn as E m minus E n by h cross. You can easily identify what this means. It means that if an electron goes from the mth state to the nth state, this energy divided by h cross is the frequency of the photon that is emitted, which is omega m. So this can be then written as e to the power I omega mn t a at the initial time. This is how Heisenberg was actually proceeding. This is actually the transition frequency. Now, we have already obtained this, so we can apply that on x. So x at any time mnth element at any time then will be equal to x operator mn at the starting time times e to the power this particular quantity I omega mn t. So if I somehow can calculate the initial matrix elements, then we can find out the time varying matrix elements using this equation. So the whole problem then boils down to calculating the initial matrix elements. So we will now work on the initial matrix elements, and we can also take a double derivative of this to obtain an equation something like the one that we obtained and numbered one. So take a double derivative of this. So t2 dt2 of x operator mn at time t, this will become I will come once, second time derivative I will come twice, so it will become minus, it will be omega mn square, it will come twice, and then it will become x mn at 0. Okay, e to the power I omega mn. So we have two equations. So basically, this is actually I can substitute that this is the this is actually this. So I can shorten this. I can simply delete this and write it as at time t. All right. So now we have got two equations. This is, I can call it 2. I have got one equation up here with omega here, and omega is the natural frequency of the classical harmonic oscillator, while this is the transition frequency. I've got the same type of equation in terms of two things. So this will enable us to figure out which terms in the matrix must be 0. So what we do is we subtract 2 from 1. So what we get, or what we get is this will disappear. So it is only with this. So omega mn square minus omega square. It is x mn in the matrix at time t equal to 0. And since this is nothing but the value of the x at time 0 times this, so this can be written as omega mn square minus omega square x mn at 0 also is 0, because it is nothing but this times something which will be. So now this tells us something about the matrix elements. What are the matrix elements then? The matrix elements, I have no space, so let me clear off some space and go up there. Let me write that here. So this is how uh, our great Heisenberg was actually proceeding in order to obtain his questions. So I'll just write it up there and we'll continue with the logic. I'll once again. Uh, it was omega mn minus omega square, omega mn square minus omega square. It was multiplied by the x mn at 0, x mnth term of the matrix at time 0 is equal to 0. Now, in order for the right hand side to be 0, either this has to be 0 or this has to be 0. Okay. And for the conditions when we know that this is not 0, this definitely will be 0. Okay. So, for example, what is the transition frequency of m to m? Obviously 0. So, if this is 0, this is not 0, then this must be 0. So, that immediately gives us the conclusion that since omega m is 0, therefore x m should be equal to 0. So all the diagonal elements should be 0. Let me now write how it should look. All the diagonal elements must be 0. Now, it will exist only when the omega m is equal to omega, right? Or plus minus omega. So this immediately brings us, so it will exist, so it will be non-zero value. X mn will have where it is omega n is equal to plus minus, and omega mn is, if you notice that omega mn, if the difference between m and m is just 1, then this condition is satisfied, which means that only the first off diagonal elements will be filled up. So this will have a structure x 0 1, x 1 0, and so on and so forth. These terms will be existing, but other than that, when this difference is larger than omega, then also this term has to be 0, and therefore all these terms will be 0. So it will be a matrix where structure is like this. Okay. Now let us try to work out this structure. Okay, let us try to work out this structure. Now here, what Heisenberg counted on was his famous equation x px is equal to I. This is something that he knew. By the way, this is an operator, and therefore I cannot write this as just IH cross. I have to write identity operator here. So this is something he knew, And naturally, he also needed to know what Px will look like. So your P matrix have to be obtained from dx. The T is equal to, we have already obtained this, Px by M. So, and we know that X operator Mn term in the X operator R, the Xmn at time t0 e to the power I omega mn t. Since we know this, so we know that dx, so dx mn t dt will be, I'll get this one out. It is I omega mn x mn 0 e to the power I omega mn t. So at t is equal to 0, we can easily see, because we are only aiming at finding out what the matrix elements are at t is equal to 0. At t is equal to 0, so the Pmn, so this is Pmn operator at time t is equal to 0 by m is equal to, then it is this term I omega mn x operator mn at 0, and this t equal to 0, this goes. So we have a relationship linking what we are trying to find out in x with this. So I'll just take the m up there. I'll just I am. I have used m in the index, as well as this m is the mass of the particle. So let us avoid confusion. Let's call it m naught. So let's avoid this confusion. Good. So we have obtained a relationship between the x matrix elements and the p matrix elements at time t0. So therefore, since they're directly related, wherever the matrix elements of X are non-vanishing, the matrix elements of P should also be non-vanishing at the same locations. At other locations, it should be 0. This equation tells us that. Okay, so now what we would do is, we would use this equation and say, let me get some additional space here. That right. Yes. So this implies that x p, this multiplication at the mth position, x and p matrix multiplied, their mth position minus px, its mth position, should give rise to IH cross. Okay. And from the structure of the matrix will look like this. Matrix will look like this. You can easily deduce that this will the diagonal. We are talking about the diagonal elements now. So the diagonal elements mm. If we talk about the diagonal elements, then it is only this. So this can be easily deduced as it is I m naught omega mn, and then it is X, I'm talking about the multiplication of this and its diagonal element, the product matrix's diagonal element. In this one case, it will be 0, 1, x 1 0. This term will be minus x. If you really do this multiplication, you will find it. I'm not going through the whole thing. X 1 0 plus x 1 2 x 2 1. This term will be similarly minus x 1 2 x 2 1 plus x 2 3 x 3 2, and then you will be able to write these terms as IH cross. So effectively what happens is that and close the matrix. What happens is that your x 0 1 x 1 0 term here becomes I cancels off, but it becomes H cross by here m naught omega. There was a 2 somewhere. Was a oh, it was a 2 here. Yeah. Because if you do that, it will come like 2. So there was a 2 here. And then you can also write the other ones. This one will be in a similar fashion, it will be right, and then you will be able to solve for them. As you solve for them, you will be able to figure out what individual elements are. So this will become, if you solve it, this is a bit longish. I'm not going through each step. I'm just telling you how it can be done. You write this and then you solve for these individual elements, and then solving you get x1 2 x2 1 will become twice h cross by twice m naught omega. x2 3 x3 2 is equal to 3h cross by twice m naught omega. So that at the end of the day leads to the two matrices x naught at time 0 will become h cross by twice m naught omega. Then the matrix will look like zeros in the diagonal. In this position, it is square root of 1. This position is square root of 1. In this position, it is square root of 2. In this position, is square root of 2. In this position, is square root of 3. In this position, is square root of 3. I have told you how to do it, but I did not show each and every step of it. You can easily repeat that step at your own time and check out where you get these numbers from. And once x is known, I also know that the p's are easily known by multiplying with this. So the p matrix also becomes simple. The p matrix at time t 0 0 0, it will become m naught omega h cross by 2, and this structure will be, the diagonals will be 0. In this position, it is root 1 I. Here it will be the conjugate of it, minus root 1 I. This one is root 2 I. Root 2 I. This will become minus root 2 I, root 3 I, minus root 3 I, and so on and so forth. So this is how he obtained the X matrix and the P matrix. By the way, you may have noticed that what we have obtained now is different from what we obtained as the X matrix earlier. The reason is that earlier, when for the purpose of computation, we wrote the X matrix, we wrote it in the X basis, while now we are writing it in the energy basis. So the energy basis, the X and P matrices will be different, quite naturally. Now the question is, can we then, let me do this, can we then obtain the results that we obtained for the we had earlier obtained for the harmonic oscillator? You'll notice that X square Mn uh, and the diagonal elements. So Nn, then you have to multiply this matrix twice and figure out what the diagonal elements will be. The diagonal elements will not be 0. So this is X, this matrix is nth element, and this will be actually sum over k, X n k, X k n, and that will turn out to be X n comma n plus 1, X n plus 1 comma n plus X n minus 1 times X n minus 1 n. And these elements we know, so we substitute. It will become n plus 1 h cross by twice m naught omega, that's the first one, plus it will be n, it will be n h cross by twice m naught omega, and when you add these two, it will become twice twice n plus 1 h cross by twice m naught omega. So when you have obtained this, the rest is somewhat simple, because all you need to do is to write the p also. P square n will become in a similar fashion. I'm just writing the result. M naught omega twice n plus 1 h cross by 2 just. And so the Hamiltonian, no, I don't have space here. I'll just write it up there. I'll just delete this so that we can work. The Hamiltonian its H operator Nn will then become 1 by twice m naught omega by 2 twice n plus 1 h cross plus, I'm running out of time, so let us finish today, omega square by 2 twice n plus 1 h cross by twice m naught omega, and that simplifies to twice n plus 1 h cross omega by 2, which is exactly the eigenvalues. N term are the diagonal elements. These are the eigenvalues, and eigenvalues we have found as n plus half, something that we already know, h cross omega. So this is the other way of obtaining the eigenvalues of the Hamiltonian matrix that we had obtained using the Schrodinger picture earlier. So this is the way Heisenberg's way of obtaining the same results. What will be the observable quantities of energy? He could obtain this way, and he could obtain for the other three-dimensional pictures and things like that. So this is how we actually use the Heisenberg picture. By the way, the matrices that we derived, that we derived, no, not this one, the square root one and I square root one and all that, that matrix can also be derived using the uh, using this picture. The first element should be psi naught x psi naught. The second element will be psi naught x psi 1. So if you know these eigenfunctions, you can easily obtain that matrix. Hmm? So that's another possible way of obtaining. You can always do that at your own leisure time. So today I just tried to illustrate how one actually applies the Heisenberg equation of motion, and that can be used to solve various systems. And its application you will actually see in the next year when we come to mainly the perturbation theory. Hmm? But other areas are also there where you need to use this method of thinking, method of picturing. Well, in the next class, you will see that there is a third uh, picture. The Schrodinger picture says that your psi varies with time and the operators remain constant. The Heisenberg pictures says that the psi remains constant with the operators varying with time. And there's a third called interaction picture where both vary with time, but that is also has many advantages. That picture has many advantages when it comes to actual computation. So I'll deal with that in the next class.